Hi everyone, I am Dr. K.S.Rangasamy, Professor, Department of Mathematics, K.S.Rangasamy College of Technology, Tiruchengood, Tamil Nadu, India. Today we will see the topic Cauchy's integral theorem and Cauchy's integration formula. So before going the Cauchy's integral, I give the small introduction. The Cauchy's integral theorem is a fundamental result in complex analysis. It states that the line integral of an analytic function over any closed contour in a simply connected region is 0. This theorem highlights the special properties of analytic function and forms the foundation for many important results in complex integration. That is, integral C f of z dz equal to 0. The applications of Cauchy's integral theorem used to evaluate complex line integral over closed contours. And the second application helps in proving that integrals are path independent for analytic functions, forms the basis for important results like Cauchy's integral formula, Taylor series and Lorentz series, and useful in simplifying complicated integral in complex analysis. So now we see the Cauchy's integral formula. The Cauchy's integral formula is a direct consequence of Cauchy's integral theorem. It provides a method to evaluate the value of an analytic function at any point inside a closed contour using only the values of the function on the boundary. This formula plays a central role in the study of analytic function, that is f of z0 equal to 1 divided by 2 pi I integral C f of z minus z0 into dz. So now we see the applications of Cauchy's integral formula. The first one, used to find the value of any analytic function at any point inside a contour, helps in evaluating complex integral easily. Used to find derivatives of analytic functions of all orders. The last one, play an important role in series expansion and residues theory. So now we see what is the Cauchy's integral theorem. If f of z is analytic and f dash of z is continuous inside and on a simple closed curve C, then f of z dz equal to 0. So now what is the Cauchy's integral formula. The f of z is analytic within and on a simple closed curve C, and z0 is any point inside C, then f of z0 equal to 1 divided by 2 pi I integral C f of z divided by z minus z0 into dz. This is called our Cauchy's integral formula. The previous one is the Cauchy's integral theorem. So now we see the first problem. They evaluate integral f of the function f of z is dz integral C dz divided by 2z plus 3, where C is the circle, the modulus of z equal to 2. So now we see the solution. Here we know the Cauchy's integral formula. The f of z z0 equal to 1 by 2 pi f of z dz minus z0 into dz. They compare this Cauchy's integral formula and our given problem. So we know that the 1 by 2 pi is missing on the left side. Therefore we can take over the right side. The f of z0 into 2 pi I, the integral equal to integral f of z minus z0 into dz. So now we see that the first equation and our given problems both are we have the equal. So therefore we are applying our Cauchy's integral concept here. F of dz 2z plus 3 equal to 1 by 2 into dz z plus 3 by 2. So now we identify what is our pole value on the z. Therefore we remove that the 2 is a constant, therefore 1 by 2 we will write dz divided by z plus 3 by 2. So now we know that the given problem is converted to 1 by 2 into integral dz divided by z plus 3 by 2. So now we see that our f of z value, the numerator value is called the f of z. Therefore the f of z value here, this problem is a 1. And our point z minus z naught, our concept, therefore z naught value is the minus 3 by 2. So now this minus 3 by 2 is compared to our given circle, the modulus of z equal to 2. We compare this modulus of z equal to 2 and our given point is a minus 1 by 1.5 is converted to modulus of value, therefore 1.5 is the less than 2. Therefore the given problem point and our circle value is the inside the circle. Therefore we determine this problem, the integral dz 2z plus 3 equal to 1 by 2 integral c dz 2 plus 3 by 2 is the equal. So now we see that our problem is equal to 1 by 2 into our problem is now converted, that value will become 2 pi I into f of z naught. Here f of z naught value already we know that minus 1.5. This 1.5 is substitute our function of value. Here the function is only 1, therefore our f of z value is a 1. Already we know that 1 by 2 into 2 pi I, we cancel 2, the value will become pi I. The pi I into 1, the answer will become pi I. So therefore the final answer, our problem f of integral dz 2z plus 3, the answer will become pi I. So now we see the one more problem, the evaluate integral c dz z minus 2, where c value is a modulus of z minus 2 equal to 4. So now this problem we know that z minus 2 equal to 4. So we see that the graph, our circle value z minus 2 equal to 4 means, so we see that this graph z minus 2 means, z means we know that x plus iy, the minus 2 equal to 4. So now we equating x minus 2, that is a real number, plus iy equal to 4. We taking the root of values x minus 2 on whole square plus y square equal to 4 square. These are the our value. This value will become, draw the graph 2, 0. That's why the x minus 2 and y minus 0 equal to our radius will become the 4 square value is of 4. So these are our point. So now we see that our Cauchy's integral theorem, f of z naught equal to 1 by 2 pi I f of z minus z naught into dz. We know that here the missing term is the right side value 2 pi I is the missing for our problem. Therefore I taking the left side, that value integral dz z minus 2 equal to 2 pi I into f of z naught. F of z naught, f of z equal to 1. Here we know that z naught equal to our given problem value is 2. So therefore we compare this z naught point in our given circle, the modulus of z minus 2 equal to 4. The value already we define z minus 2 equal to 4. Our value will become the inside the circle. Therefore we will continue this problem in the Cauchy's integral formula. Our f of z value here only 1, therefore here our point is the 1, therefore our f of z naught value here also 1. So these ideas we applying again the 2 pi I into f of z naught, and the values will substitute f of z naught equal to 1. Therefore you multiply 2 pi I into 1 is the 2 pi I. The final answer, our problem is a dz divided by z minus 2, the value will become 2 pi I. Thank you for watching.